Yeah, started.
Okay, so welcome everyone to the second and also the last talk for today in the conference. Very happy to have Anton Mellit of the University of Vienna, and he'll speak about old and new identities for the Nabla operator and counting affine permutations. Anton.
Thanks a lot for invitation and for the opportunity to speak. So I should mention that this is a joint work with Erik Carlsson. Okay, so let's begin with some notations, some of them standard. So I will sometimes talk about variables, and there are two kinds of variables. Some of the variables I call parameters, Q and T, and then there are infinite sequences of variables, usually X and Y. So I denote by capital letters the whole sequence, and this I will call alphabets. And I will talk about symmetric functions. And to fix notations, there are elementary symmetric functions, complete homogeneous symmetric functions, and here is the power sums. These symmetric functions are indexed by integers, and there are functions indexed by partitions. So now if lambda is usually a partition, and you write E lambda for the product of the individual E lambda i's, and the same for H and the same for P. And then there are other symmetric functions like the monomial. Symmetric functions is a sum. You write the you take xi to the lambda I, the product, and then take all permutations, all distinct permutations of such monomials. For example, the M with a single part is just the power sum, M with all ones is just elementary. And then Schur functions can be defined as a sum over semi-standard Young tableau of shape lambda. And in particular, S with a single part is just a complete homogeneous function, and S with all ones is the elementary function. So standard, and I will talk about modified Macdonald polynomials. So this is a notation. It's indexed by partitions, and they can be defined as unique symmetric functions satisfying this overdetermined system of constraints. If you do this operation, so I will talk about Platistic substitution later, but this, for now, you can just take it as a black box, some kind of operation. So if you do Q minus 1, then you get some linear combination of monomials and mu, where mu is less or equal to lambda in the dominance order, and the same. And for T, if you do it with T, then you get the same, but for the conjugate partition. And this kind of gives you one-dimensional space of symmetric functions. And to fix it, fix uniquely, you need normalization, and this is a normalization condition. So these are the modified Macdonald polynomials. There will be some example just a little bit later. And I'm not going to talk about Macdonald polynomials themselves, but more about operators defined in terms of them. And this is a Nabla operator introduced in a paper by Bergeron and Garsia. And they are defined somewhat indirectly, since Macdonald polynomials form a basis of symmetric functions. It's enough to define how any operator, how it acts on the basis. And this is the condition that each Macdonald polynomial is multiplied by a certain monomial depending on the partition. And here is a monomial Q to some power, T to some power. These are the powers, usual statistics of partitions. Now, the first, any questions up to here? Any confusions? So first interesting fact about this operator, although it is, if you want to compute it, as you will see in the example, in order to compute it, you need to use rational functions in Q and T, but it turns out that applying Nabla to any symmetric functions mentioned above, you get a polynomial linear combination of symmetric functions without any denominators. And more precisely, if you apply to M or E or H or S, you get again span of you get a combination of the same kind of functions with coefficients at polynomials in Q and T with integer coefficients. So once you have this kind of property, you start wondering, what if the coefficients of this polynomial coefficients count something? Or maybe they are positive or negative, but in any case, maybe there is a combinatorial expression. So let's give some examples. So I remember by heart these two Macdonald polynomials, H2 and H12 of degree 2. You see that to pass between 2 and 1, 1, you just need to switch Q and T. Anyway, so you can see that you can write it like this, or you can write it in terms of H2 and E2. But you see that this is not, the base change matrix is not invertible matrix. I mean, not invertible as polynomial matrix. And therefore, for instance, to compute E and H in terms of the Macdonalds, you need to do some division. So here is E. I just took the difference to kill H2 and then divide by Q minus T. And here is H2 in terms of the Macdonalds. Now using these formulas, you can compute the Nabla. So when I apply Nabla to E2, I have to multiply H2 by Q and H11 by T. So I get this formula. And after you substitute, you get some cancellations, denominators cancel, and then you get this nice combination. And if you apply Nabla to H2, you get this nice combination. And already here you can see that first one is positive and the second one is negative. Well, you can easily do this exercise at home to compute the powers of Nabla applied to E2 and H2. And again, you get positive in the first case and negative for the second case. Okay. So what do we do with this? So we want to understand, to apply Nabla to some functions and to try to find some explicit expansion, combinatorial expansions. And the first such thing was considered Nabla of En, because Nabla of En computes so-called the character of diagonal coinvariance. And this paper by Haglund, Heyman, Loehr, Remmel, and Ulyanov, there was a explicit combinatorial formula conjectured for this Nabla of En, which is also the character of diagonal coinvariance. And this formula I proved together with Erik Carlsson in 2015. And the formula looks like this. So Nabla of En on the left-hand side, and on the right-hand side is the summation over combinatorial objects, which we can formulate differently, but I like to say that this is a Dyck path, pi, and W is a sequence of integers, so-called word parking function. So here is an example of a Dyck path for n equals 4. And here is an example of a parking function. It's some labeling which you usually attach to vertical steps of the path. And then what you do with this pi and W, you put W in the to form xw, so product of the corresponding variables. And we have t and q, and t is just counts the area of the Dyck path, which is a number of squares between the path and the diagonal. And dinf, q to the dinf, and dinf is more difficult to define. There is some sum over pairs of labels which satisfy some inequality and sit in certain relative position. So this is the shuffle conjecture. If you are wondering about higher powers of Nabla applied to En, this is covered by the rational shuffle conjecture, which proved a year later. So, so this kind of identities I am interested in. So now one thing that is very big motivator is the Nabla positivity conjecture. And as I mentioned, if you apply Nabla to H2 or to E2, you got positive or negative expressions. So it is very strange property. And when you start applying it to other Schur functions, you will notice the following observation. So applying any power of Nabla to a Schur function gives you a Schur positive expression, but up to sign. So the sign depends on lambda, and lambda. So how do you determine the sign? You draw lambda as a diagram, and you draw this red line, which is, I call the main diagonal. And you count how many boxes are over the main diagonal. In this case, we get 1, 2, 3, 4, 6 boxes. And this is how you determine the sign. If you remember the example, then for H2 you would get for H2 you have this picture which has 1 box over the diagonal, so the sign is minus. And for E2 the picture diagram is like this, so there is no boxes over the diagonal, so the sign is plus. And so this Nabla positivity conjecture is open. But in special cases, when lambda is a hook, in other words, this sort of shape, in fact it follows from the so-called compositional rational shuffle theorem, which was in fact proven. And this, in more generally, this compositional version, it gives you formula for Nabla applied to so-called whole-Littlewood functions, and then you can combine them to get hook Schur functions. And in particular, we deduce this propositivity property. So just to summarize this introduction, motivational part, we want to compute Nabla. Now, since we have it, you see we applied Nabla to EK. After some time, you start thinking, can we just compute it somehow, Nabla of anything? And and this is the motto, so to say. We want to compute sort of Nabla as an operator, not as individual evaluations of Nabla, so some particular functions. So how do we to understand what it means to compute some operator? I need to recall the Cauchy formulas, the idea of Cauchy formulas. So for that, I need to remember the whole scalar product. So it can be given equivalently by three different formulas in terms of Schur functions, in terms of H's and M's, or in terms of P's. So this z lambda is a constant. This is given by this sort of formula. Yeah. So this is a defines the scalar product on symmetric functions. Any questions? Okay. Please interrupt me just by voice. It is the best. I like interruptions. So I think I'm going too fast.
Maybe I have a question.
Yeah.
Can you motivate the eigenvalues that this Nabla was given? Because I guess the way that you define Nabla is by these particular choices of t to some power, q to some power. Why is this a? Can you motivate why this is a reasonable definition?
So I think I can motivate it by saying that the similar things were observed where you, so in general you draw your lambda. Wait, how does it work? So you draw your lambda, something like this, and then you put numbers, you put monomials in the cells by putting 1, then q square, q cube, t square, qt. You understand the idea, right? Just q to the I, t to the j. And then it turns out that this factor is q to the n lambda prime, t to the n of lambda is just the product of all cells of these things. And it turns out if you take other functions of these things, you also get nice properties. So sum of, for instance, also is nice. Will give you a nice operator, meaning that, for instance, it will have this property that applying it to any m lambda, you will get a combination with polynomial coefficients and so on. So maybe this, from the combinatorial point of view, this is I think good motivation. Why this?
All right, thanks.
So
Yeah.
for summation, the Schur positivity also will be true.
Oh no, not, I don't know about positivity. I don't remember. Not positivity, but integrality, that the integer coefficient, that will be true.
You mean that the result will be the polynomials in Q and T, right?
Yeah. Mm-hmm. But there is this one for the sum. It is much simpler. There is some explicit Platistic formula for this operator, and it's much simpler. But for the product, there is no such formula.
And no representation theoretic background of this formula.
Okay, then if you want, well, there are many points of view, right? You can think for geometric interpretation in terms of the Hilbert scheme. There will be some natural interpretation. For representation theory, if you think about interpretation of Macdonald polynomials via quantum groups, like this Kirillov, I think of Kirillov, there will be also interpretation of these operators. So these operators appear like everywhere. And yeah, another thing, they're part of an algebra, interesting algebra of operators called elliptical algebra, which is also interesting.
And so these are particular operators of the elliptical algebra, right? So
Yes. Yeah, depending on your background, I will tell you why it should be interesting for you, but I don't even see who you are. So.
I'm Anton Khoroshkin.
Okay. So
I have listened about this operator from Zhenya Gorsky a couple of times, and each time it was really quite fancy. So
yeah, so in different realizations, they have different meaning.
yeah, okay, great. Thanks a lot.
So I was talking about this Cauchy formula, and of course, whenever you have a scalar product, you can look for different orthogonal bases. And the magic of there is some kind of thing, maybe if you have seen it, it is obvious. If you haven't, it is miracle that if you form sums like this, So now I use two alphabets of symmetric functions, x and y, and you form sums like this, they will all be the same. So if you write for Schur's, you just take sum s lambda s lambda. For h and m, you write this sum. For p, you write this sum. You should see the logic. You put as a first in x, you put any thing that is on the left of your scalar product, and then you put something which is on the right of your scalar product to make one, to make scalar product equal to delta lambda mu. And so it's called dual basis. And it will, so the magic somehow is that this all functions are the same, this three formal functions that I wrote. And now if you want an explicit formula for this function, you, in terms of xi's and yj's, for instance, if you use this formula, you can easily get this expression that this Schur, this is called Cauchy kernel, this function in two sets of variables, is just a product of 1 over 1 minus xi yj. And another way to think about it is to take hn of the product xy. So what do you mean by product xy? Product of two alphabets is just, you take all pairwise products. Like here, x1, y1, x1, y2, x2, y1, x2, y2, and so on. Take all pairwise products and you plug it into this hn. And from this we obtain that different formulas for this hn of xy. One using Schur functions, sum over partitions of size n. Another, oops, there is a mistake here because it should be h and m. So m, oops, m lambda, or in terms of p's, p lambdas. And if you want, notice that in terms of the p's, you can also connect it to the exponential, so-called Platistic exponential. Yeah. So, right, so this is h of xy, and there's three expressions for it. And there is another way to say what it is hn of x times y using formalism of Platisms. So what is this Platism? It tells you how to define when you take f, a symmetric function f, and some expression e, and what it means to evaluate f at e. You just have to write f in terms of power sums and replace each power sum by this thing en, where en is obtained from e by raising every variable to the nth power. So this is what Platism means. The example is here. So h2, to compute h2 of whatever expression, I wrote here 1 over 1 minus q, for instance. You write, express h2 as p1 squared plus p2 over 2. And then you need to evaluate it at 1 over 1 minus q. P1 gets replaced by 1 over 1 minus q, and P2 gets replaced by 1 over 1 minus q squared. And then you get this nice formula. And this is a formula also for H2 evaluated at a sequence 1, q, q squared, q, q, and so on. So all this Platistic formalism guarantees that no matter how you do this evaluation, using this definition, like expanding 1 over 1 minus q as a generating series, or using this abstract algebraic recipe, you get the same answer. Anyway, so this is what Platism means, and this is what I meant when I wrote, you remember that q minus 1x in the definition of Macdonald polynomials, t minus 1x, this is where it comes from. So this Macdonald polynomials, it is a formal consequence of those properties, is that they are orthogonal with respect to the modified scalar product. So the modified scalar product is defined by inserting some some Platism in the usual scalar product. I'm not writing it down. I'm just writing the corresponding Cauchy identities. That there's 3 ways to write this generating series for the modified scalar product, which is so it will be Hn, but over instead of just Hn of xy, it is Hn of this xy over with the denominator. And by the general theory, no matter how you write, no matter which pair of dual bases you choose, you get expressions. So one expression is this one with H and M. You can write it as S and S, or you can write it with power sums. So you see that power sums are orthogonal. And Macdonald polynomials are also orthogonal, but this, so there is this Z, now depending on Q and T, and there is an explicit formula for the Z. And so it is a scalar product of H with itself with respect to modified scalar product, and there is this formula with products of arms and legs. If you have seen it, then you will recognize it. If not, you can look it up. So, right. So we have this Cauchy kernel, some generating function in 2 sets of variables. And how do we use this? When we want to understand some operator, we just apply it to your Cauchy kernel, and you get a generating function of your values of your operator on different functions. So think about it. You operate, for instance, you apply, so we want to apply to Nabla, and we say, so Nabla was defined with 1 set of variables when we have x, but if we have x and y, we just ignore y and we only use x. So Nabla acts with respect to x variables, and then by this general theory that I'm explaining, Nabla of this Hn of xy over q minus 1 minus t can be written, for instance, as follows, as this. So you can see that if you, for instance, you compute this function in some way, then you can interpret the result as you expand it into the basis S mu of y, and then the coefficient in x are Nablas of S lambdas. So you convert the problem of computing Nabla of S lambda into the problem of expanding the same function into different bases, the same function in 2 sets of variables in different bases. So you see that this contains, so if you know Nabla of Hn of this in some form, then it contains information about all Nabla of S lambda, but in a somehow not a so explicit form, because the coefficients of expansion are this S mu of y over q minus 1 minus c, which are not very, you don't know them somehow, and that's the logic. But think about it. If we manage to perform the substitutions, somehow compute substitutions of this function, when we substitute y instead of y, q minus 1 y, and afterwards instead of y minus ty, then we win. We will obtain the formula for Nabla so we win means that we will have a formula for some Nabla of S lambda of x, and the coefficient is simply as mu of y. So if you have a formula for this, and in the computer you expand it in the Schur basis, you just get your Nablas of S lambda on the nose. Okay, so
but the meaning of this formula is that you apply Nabla for x's, right? For
yeah, and always for x's. Let's agree that. So this leads us
Sorry,
to the
I'm a little bit confused because your call sheet, you have a lambda and a mu in there on the Schur side. I mean, is that what you want to write?
no, and it's not what I want. Thank you. This correction is that it is lambda, of course. Right.
And would that also not affect the expression
No.
you write?
It's a mistake. Yeah. Right. Of course. I mean, that's. I just. I hope I didn't make this mistake. Right. Of course, you want to know Nabla of S lambda, so you expand it. You collect the terms instead of in front of S lambda of Y, and that's what you want. Yeah. Sum over lambda. Okay, so yeah, that was the mistake. Is any more confusions? No. So the this leads us to the question: what do we know about Nabla of H in n of x, y, q minus 1, 1, I think. So how can we compute it? And that's what we are going to do. So I probably should write here. So how do we actually compute it? We compute it as not express this. So what we want to do, we want to write number hn of x, y over q minus 1, 1 minus t. Let's do this exercise. So you write it's a Nabla of sum of lambda by the Cauchy formula that I have. This is Macdonald polynomial on x, Macdonald polynomial on y over z lambda qt, right? And now we need to apply Nabla to Macdonald, but this is from the definition. We know that this is q to some n of lambda prime, t to n lambda, h lambda of x, h lambda of y over z lambda. And in fact, it turns out that there is a nice, so besides the fact that q to this power and t to this power is a product of the cells of the partition, there is also a nice formula using just Macdonald polynomial itself to sign. Which is just this. So this turns out to be simply the factor of the Nabla. So in fact, if you write something like introduce a third set of variable, like call it W, for instance. So formula for this. So formula for this would solve many problems. Okay. But I don't promise to give you a formula for this, and I will give you a formula for this in the next page. Okay. So yeah, you see, or even more, put more Macdonald polynomials and more sets of variables and form this summation. That's my favorite generating function. Let's call it master function. Nekrasov partition function, or many names. Okay. Okay, that's so let's go to the next page.
And what do you mean by formula for this? You mean a kind of Cauchy kernel or some?
No, I mean so here this is a formula for it, but Macdonald polynomials are somehow not very explicit things. What I want is some kind of sum over some combinatorial objects. I don't know, some explicit combinatorial sum.
So you mean like expression in terms of summation and products of some visible
Some
things?
more elementary functions like Schur functions, monomial, homogeneous functions.
But the summation of the product.
So this is a sum of partitions of products.
No, my question is what kind of formula you are looking for, because for the Cauchy kernel there's a good expression in terms of the product, like product of 1 over x,
Yeah, well,
y.
Well,
So the question is, the formula is you're looking for is the expression in terms of sums or over some partitions, or maybe.
Well, I think you should have. I expect to have both. There should be a good sum formula and good product formula, and that's so there's this conjectures of Hauser, Letelier, and Rodriguez-Villegas. From those conjectures, it follows that actually there's a product formula. Okay, but I think for me, sum formula is good and product formula is even better.
But the conjectural product formula is known, right?
But it's not explicitly combinatorial. That formula involves some coefficients of some Hodge polynomials, which we don't know.
And can you give a reference for that? Or?
This is so Hauser, Letelier, and Rodriguez-Villegas. Rodriguez-Villegas called arithmetic. I think arithmetic Fouriers or some character varieties. I forgot the name of the paper. So they write this kind of sums, and they take Platistic logarithm, which means decompose it into product and connect it to mixed Hodge polynomials of character varieties. Okay,
thanks a lot.
Yeah. So let's go further. Right. So the way I propose to write this, to compute these expressions, this Cauchy Nabla of the Cauchy kernel is so we have this geometric interpretation of Macdonald polynomials. So what this geometric interpretation about? Let's go to step back to a simpler situation where we have we set t equals 0. If you set t equals to 0 in Macdonald polynomials, you get modified Hall-Littlewood polynomials. These ones. So you just t equals 0. So if you express this modified Hall-Littlewood polynomials in the monomial basis, and they take the coefficients, these coefficients have explicit geometric interpretation. Sorry, this is not Kostka polynomials. If I express this into Schur's, then it would be Kostka polynomials. And these coefficients are the same as if you express Schur's instead in terms of usual Hall-Littlewood. And this, because of this Cauchy kernels, it's all the same. So yeah, anyway. These are somewhat similar to the Kostkas, but they're not Kostkas. So this K you get as follows. First, you have to go to a finite field. There are ways to formulate everything over complex numbers, but somehow more direct. It is simple is over finite fields. So you consider n-dimensional vector space over Q, finite field with Q elements. So Q is the power of P. Say power of P. Let's say P equals 5 or 7 or something like prime number. And this you count flags. So flags of vector spaces. So F0 is always 0, FL is the whole thing, and then in between you have several vector spaces, and the dimensions are fixed by this partition mu. So this partition mu will always correspond to dimensions of the flags. And what does lambda stand for? And there is an extra condition. So these flags must be fixed by a fixed nilpotent matrix n lambda. And what is this n lambda? So and lambda is like this. It is block upper triangular. It is zeros on the diagonal blocks, but it is 1, 1, 1, 1 on all ones, one above diagonal blocks. And the sizes of blocks are lambdas, lambda i's. In this way, you can write any nilpotent matrix after conjugation. For instance, if lambda is n, then n lambda is a 0. If lambda is 1 n times, then it is just Jordan block, this kind of matrix. And all others in between. So this, you count these flags and you get a polynomial in Q, and that's your K M lambda. And if you do it over complex numbers, then it will turn out that this space of such flags can be paved by affine spaces, and you just count how many affine spaces of each dimension you have and you put it in a genetic function. Then there is another way. So when you have this, you have nilpotent matrix and you count flags, you have geometry here. You have all nilpotent matrices of the same type are conjugate, and all the flags are conjugate. You can rewrite this summation, this counting as a, instead fixing alternatively you fix the flag. You can fix the flag to be the standard flag, and then you will be counting nilpotent matrices. And so up to this K, up to a certain explicit factor, rational factor, is number of n, matrices n, such that n is conjugate to n lambda, and n is block apotriangular with blocks of sizes given by mu. Okay. So there's two different ways to get whole Littlewood polynomials. And this result that I'm referring to tells you how to get Macdonald polynomials in a similar fashion. And of course, so this is a bit more complicated, but in one sentence, the idea is to replace matrices by matrices with polynomial coefficients. But then, of course, you have to fix, but there will be more things to fix and more. So how to get Macdonald polynomials? So let's denote by K M lambda Qt the polynomials in the expansion of Macdonald in some monomial basis. And it will turn out that Km lambda is up to some explicit rational factor. It's given as follows. So now it will be summation over tuples M1 up to Mn. And what you will be counting some nilpotent matrices, and you will divide it by the automorphisms. So I'm just here trying to explicitly combinatorially explain this counting. More geometrically, you can say there are some vector bundles on P1, and you count in the morphisms of those vector bundles. But explicitly is as follows. So mi's are positive and non-negative integers. I's are non-negative integers, and t is always raised to the sum of mi's. This will be always the same, and the rest will depend on q. So what is this n's? N's are polynomial matrices which polynomially depend on z, and coefficients are also in the finite field. The condition we had before that n is conjugate to n lambda now has to be said that n is conjugate to n lambda over the field of rational functions. So this is how dependence on lambda is encoded. And then you said, so n will be polynomial nilpotent matrix, and these automorphisms will be polynomial invertible matrices. And the conditions are now involving m. And instead of saying that before the condition was that matrix is upper triangular. Now we put a restriction on the degree of polynomial entries. And in the upper triangular part here, we use, for n, we use the difference. So each cell in this matrix will have corresponding I and j, and so have mi and mj. And so there is this inequality. So, and this is required over the diagonal. And under the diagonal, you ask this inequality to hold slightly stronger, one stronger. So you see that here degree is -1, but there it is -2 over below the diagonal. And the same kind of idea holds for out, but just that we have we don't have that -1 here. So over the diagonal we have inequality with mi minus mj, and under the diagonal you have this one stronger inequality. And that's the formula for the Macdonald polynomials. So again, so automorphisms hold. For automorphisms, you just use the difference of mi and mj. For instance, if LMs are the same, then out will be upper triangle, block upper triangular, and n will be only non-trivial where there is difference mi, where mi's are different. So, well, or n is 0. That's a special case which is also contributes. Then it satisfies all the inequalities. So so we count this sort of block upper triangle matrices of polynomials where you have inequalities on polynomials, on degrees of polynomials. Yeah. So this is a formula for a single Macdonald polynomial. And this is because, but there is a more general formula is true. So you should think that these conditions, the degree is less or equal mi minus mj minus one more, is a condition at infinity. That, like, normal condition would be that degree is less or equal mi minus mj, but you want at infinity the coefficient, the value to be 0, and the value at infinity is like the leading term of your polynomial. So these are conditions at infinity. Instead, you can also impose conditions at other points of P1. And if you start imposing other conditions, then at those other points, you can also choose a flag. You can, and then you will say that, so this kind of summation will correspond to a product of Macdonald polynomials with some rational factor. You can get as many Macdonald polynomials as you want by inserting more and more points, right? But so for us, for our talk, it is enough to have one more point, and we can say take 0 point. So you will say that some entries of your matrix of polynomials will have bounded degree and also bounded degree from below, from like must be divisible by x, must have 0 at order of some orders. So it turns out, so in this case, we really will obtain the formula for, we'll obtain a product of 2 Macdonald polynomials with z lambda in the denominator.
But that's now an expansion in terms of monomials again?
Yes, this is in terms of monomials. And now the point when you have this enumerating these matrices which are nilpotent, it is very difficult to count matrices which are conjugate to given nilpotent matrix. It's much easier to count all nilpotent matrices, and it's precisely correspond to summation over lambda. When you ignore the type of the nilpotent matrix, just say matrix is nilpotent. So, and then it turns out that, so doing this kind of summation with this n and m, with this n and this out, this like doing this summation here will precisely overall nilpotent matrices will give us the generating function that we need. That is for the Nabla of the Cauchy kernel. So this is the first new result obtained from here. So on the left we have first power of Nabla applied to the Cauchy kernel, and on the right we have this sort of expression. So
but now you are using 3 points.
No, 2 points.
How are you getting the h minus 1? How are you getting the Nabla part?
Okay, so if the Nabla part corresponds to saying that I want to choose another third point, let's say point 1, and I want my matrix to vanish in that point. And therefore, if you want your one matrix vanish at that point, means all your polynomials are divisible by z minus 1, and you can just remove z minus 1, and that the rest will just have a one stronger restriction on the degree. And so inserting Nablas correspond to
Okay, so you're secretly using 3 points, but you're throwing it out.
Yeah, I'm secretly using. Yeah. So this minus 1 correspond to, if you use minus k and minus k minus 1 instead of 1 and 2, you would get Nabla to the k. Yeah, that's in this, use these properties, but just replace 1 by k and 2 by k plus 1. Yeah, and then so it turns that then counting matrices of polynomials is simply you get some polynomials with some restrictions on degree. You get just the power of q, and then after some fixing details, we arrive at this formula. So the sum is over triples of vectors m, a, and b. M is just as before. M is non-negative integers, but a's and b's are between one at greater or equal to 1, and a's are, so in the formula you get t to the m. This is the sum of m's, and a and b go into the monomials xa and yb. Xa is a monomial product xi ai, and yb is similarly from b. And naturally this xa is because, so a correspond to 0, b correspond to infinity on P1, x correspond to 0, y correspond to infinity. And then when you compute the contribution of how many nilpotent matrices you have divided by how many invertible you have, some power of q will cancel, and that's what you're left with. So there is this q to the dinf. This q to the dinf is some explicit statistic depending on m, a, and b. And then there is, this is clear, and mu is the multiplicities in this triple. So you have this triples m, a, b. They are considered up to permutation, simultaneous permutation of the entries, and some of these entries may repeat. So triples of entries may repeat, and you get a partition mu, and you take the product of factorials of that partition. That's mu q factorials of forgot q. Yeah, that's the formula. Similar formula holds for powers of Nabla. And okay, that's the first result. Now, so one way I want to stress out one way to think about this kind of summation. So it turns out that, so more geometrically, let's look at the set of affine permutations. These are maps, bijections from z to z, which are periodic. These are called affine permutations, periodic with period n. And positive means that sigma of 1, sigma of 2, and so on, and greater than 0. So they preserves the positive integers. And so this set of triples, let's try, suppose we want to find the coefficient in front of monomial, given monomial in X and given monomial in Y. That means we fix A up to permutation and we fix B up to permutation. And then the summation, resulting summation is over M's, but some of them have like up to something. So, well, it turns out that this summation over is precisely going over double cosets over the set of affine permutations modulo this subgroups of finite subgroups as A and as B. And so we have this kind of interpretation of this formula as a sum of our affine permutations. Right. So that's the thing that I wanted to say.
So can you say what DINV is purely in terms of the inversions of these affine permutations?
It's not quite the inversions. It's this something called DINV, and so.
But you can state it purely in terms of the permutations themselves. Is it true?
In terms of the affine permutations. Yes. Yeah. So okay, so there is this arrangement, and then you should the set of affine permutation is kind of separated in some chambers, and then each chamber has a certain number associated to it. But another way to say is that you so if you have an affine permutation, then this DINF sigma, DINF is like the number of I and j such that j is between I and I plus n, and sigma of I is greater than sigma of j. So the next thing is also DINF counts somehow inversions in sigma which are not too far. Okay. And for Nabla to the k only affects how far. How far.
Very good. Very good. Yeah.
So this is the one thing, and then okay. So now I started a little bit later, maybe. So the last thing I want to talk about is the formulas of Loehr Warrington formula. And I will just give you idea. So the formula is supposed to tell you of what is it Nabla over S lambda, and is in terms of sums over nested Dyck paths. So monomial expansion of this of Nabla of S in terms of sum of a nested Dyck paths. So it turns out, so the way to think about it as a sum, again, summations over affine permutations and so on, is as follows. So first is a Dyck path is a P-tableaux. As follows. So let's write the sequence, the area sequence of the Dyck path. then it is a Dyck path if and only if and only if AI is less or equal to AI plus 1 plus 1. Right? No. AI plus 1 is less or equal AI plus 1. So now let's consider a poset of z greater or equal to 0. And we say that I is less than j. If I is greater than j, if and only if is I is at least j plus 2. Instead of j plus 1, you say j plus 2. And then you consider what is a P-tableaux. Is a feeling of some shape such that if you have, let's say, x and y, then x must be not greater than y. And if x and y are like this, then x must be less than y with respect to poset. So this condition in comparison is on a using the poset relation. And then Dyck paths are in bijection with P-tableaux of shape of this shape. And parking functions are also P-tableaux of shape of the same shape, but where P is some set of pairs. I don't know, some kind of Z times n greater or equal to 0. And the relation is using the Dyck path poset relation for here, and when to break ties you use the relation comparison of integers between 1 and n. So now we have shapes, we have P-tableaux of fixed shapes which produces Nabla of e to the n, and then change shape, different shape, say lambda gives Nabla S lambda. That's so you can easily check that a P-tableaux of shape of arbitrary shape corresponds to nested Dyck path, or for when P is just the positive integers, and nested parking function if P is whatever, and this is in preparation. Okay, I think this is what I wanted to, where I want to stop. Thank you.
Thank Anton for a very nice talk. Any questions?
Yeah, maybe I just about your last sort of slide. So you have your formula, and now you started talking about the Loehr Warrington formula. And so are you saying it follows from what you've got, or are you saying it's essentially the same? I didn't quite reach the punchline.
So I still haven't decided what the punchline is. So strictly mathematically, using this formula, from this formula we can deduce the Loehr Warrington formula.
Yeah.
But more, if you want a more philosophical punchline, all these formulas should be interpreted as enumerations of P-tableaux. That's maybe the, but I don't know the most general statement. That's the more, and so it's like, and of course, so suppose so you can apply Nabla to different symmetric functions. And there is only finitely many symmetric functions of given size, given degree. And suppose you proved formulas for prove this kind of formula of Nabla applied to some enough symmetric functions that form a basis. Then automatically, because of these summations of P-tableaux, you are supposed to get all other formulas for Nabla to other functions, to whole little functions, to modified complete homogeneous functions. And but so far, I don't know the most general statements.
And I ask, we know that Nabla of En is diagonal harmonics. What is Nabla of S lambda?
Oh, you can interpret diagonal harmonics as only one. So diagonal harmonics is only. So you have some module. There is some module, some M, and you is some module over polynomial ring in X and Y variables. And diagonal harmonics is would be simply taking the tensor with C over this ring. But now take alternating sum of all Tor I of M C. Tor I. And take this sort of Frobenius character that should give you Nabla of. Yeah, and then there is some Sn action. Yeah, so and Sn. So this should give you the Nabla of S.
Where did mu come from?
So mu was okay. Oh, yeah, no, there are two Sn actually. Yeah, I didn't prepare this for this talk, so I have to think about. So there are two Sn actions. There is some module. It's easy to write what it is. You have to say that it is an image of so you take R as so you do it Sn times and you map it to this, and the map sends F and W. So F is in R, W is in Sn to sum W of F times sum of pi in Sn, pi of F. I think, yeah, I'm being a bit. I think something like this. So, right. So there is some image of this, and it's not so difficult to check that this first zero store is just a diagonal harmonics. And so there is this. There are many people also. So like.
Well, maybe I can ask my question a different way
Yeah.
as to what's bothering me. Is I know that for each diagonal harmonics, for each power of Nabla applied to En, I have a corresponding simple module for Daha, finite dimensional simple module for the rational Cherednik algebra.
Mm-hmm.
But for Nabla of S mu, I don't have any more finite dimensional modules of rational Cherednik algebra available. So where is this coming from?
Let me think. So I think there is a bimodule of the rational Cherednik algebra. So
Okay, yeah, could be. All right, we can we talk by email or something. Yeah.
So there is a recent paper by Loehr, and it's about R gamma of P tensor P and how it can be deformed to a module over the, I think, bimodule of a rational Cherednik algebra.
So
And that's
P,
the module.
P here is a Protesi bundle?
Yes, yes.
Yeah, okay. All right, I will look. Thank you.
Yeah.
Any other questions?
Yes, I have a question. Is there a connection to the QT Fuß-Catalan numbers? And could you,
QT?
the QT Fuß-Catalan numbers, the generalized
QT
Catalan
what?
numbers. Fuß-Catalan.
Sorry, I'm blocked with a key.
Okay, my connection is maybe not good. The Fuß-Catalan, you know them? Generalized Catalan, they correspond to Dyck paths with the where the slope is not diagonal but tilted.
Ah, the like MN Catalan. So the
Yes,
rational,
MN, exactly.
rational
MN
Catalan numbers.
Rational Catalan numbers, yeah.
So this is this is not even in progress, but I suspect that you just trivially modify this definition of dinf, and you should get. So you see, like for instance, in the affine permutation side, you say that dinf is number of ij such that I and j's are not in number of inversions which are not too far. In the case of rational Catalans, you should count inversions which are like not too far, but instead of just using k times n, you would go like you have two numbers, m and n. N is the period, and m is how far you count your dinf. But again, this is also not even in progress. Everything should work the same way.
Okay, thank you.
Any other questions?
Sorry, maybe I missed it, but did you explain what a P-tableaux is? I mean, sorry.
Yeah, so
I thought this was by P-tableaux, do you mean RSK P-tableaux or something else?
So this is introduced by Gesell-Vienot, I think, and then also decided by Kratenthaler, I don't know, I think, or yeah, it's kind of old, but so, and then recently Shareshi and Wachs, yeah, so P-tableaux is a filling of shape, of certain shape by elements of your poset P, satisfying these two conditions, these two conditions.
So the P there is a poset. It's not.
P is a poset, yes.
Okay, I see. Thank you.
Any other questions for Anton? Okay, if not, let's thank Anton again for a very nice talk. Okay, so that's the last of the talks for today. So tomorrow again, I think we begin at the same time as we did today. So hope to see many of you again tomorrow. Thanks.